Look at these two questions first before the other come. Is the back okay if I don't turn off the light? Can you still see the screen or you prefer to turn off the light? Okay. Is it okay? Okay. How about the rest? Is it okay? Okay, maybe I'll start from talk a little bit more about the project so that you have an idea what you need to do. Okay, so for project one, right? Okay, so I say that this is a project that is closer to pure maths. Okay, so uh, your idea should be getting from the election. Okay, or when you do tutorial or so. Okay, or when you readings. Did you guys do tutorials or not? Huh? I think some of you did it, but how about the rest? Huh? Assignment? Yeah, also assignment. How about the tutorial? I put some question on the Moodle. Yeah, you can try those question out. No, not yet. Okay. I strongly suggest you try some of them if you don't have time to try all of them. Okay. At least get an idea how to use the theory or concept. Okay. Yeah. So get the idea from a lecture or the textbook. Okay. So for example, you can pick a topic such as monotonic sequence theorem, right? Okay. So what's a monotonic sequence theorem? Can anyone recall? Kingston? Okay. So every bounded sequence convergent. Okay. So for example, we didn't show why this is true. Okay, we didn't prove that why is this true. Okay. So you can try and prove in your project why this is true. Okay. So to prove that this is true, right? So you need to set up your theory. Okay. So you need to set up some definition. Okay. You could set up the definition. For example, what kind of definition you need for this statement to understand this statement? What definition you need? Hmm. What definition do you need? Okay, for example, monotonic, right? For example, bounded, right? For example, sequence, example, convergent. Okay, so you need to tell people again what's this statement about. Okay, and then try and prove it. Okay, try and prove it. Okay, so this is the theory part. Okay, so and then the next thing I focus on is the examples. Okay, so after you introduce, you say that this theory is true or this theorem is true. Okay, how is it useful? How is it practical? Okay, how are we going to apply this in a mathematics example? Okay, how we do calculation, right? Okay, so you need to give a few examples. So these are examples in mathematics question. Okay, for example, the example we did in classes. Okay, so to tell people how to use it, and and so before this theorem, so typically we will start with some history of this theorem or background of this theorem. So for example, how is this theorem discovered at first? Okay, so how this theorem appear? Who introduced this theorem? Okay, so how you gonna find this information? One very good place to start with is Wikipedia. Okay, you can go Wikipedia and then see how they introduce it. But I'm not asking you to copy it, but Wikipedia will provide the references. Okay, so when you do references, right? I don't want you to refer to website. Okay, no website. Okay, don't uh cite. So for example, you go to Wikipedia. Okay, Wikipedia will certainly cite paper or cite the textbook or whatsoever. So you go to those reference and then read, and then cite those books. Is it clear? Okay, try not to cite any website, okay? Yeah, you can go to the website, and then the website should refer you to different book sources, and then you will go there, okay, or journal. Yeah, okay. Do you have better idea now? Yeah, if you, I also put out some examples of the previous project, which you can take a look. Okay, but be sure that before you write anything, right, come and come and talk to me first. Okay, yeah, come and talk to me first. Okay, about what project or what thing you're gonna do. Okay, yeah. So for example, one of you took sequence Swiss theorem, right? Yeah, Swiss theorem. So I prefer not to have a project overlap. Okay, so everyone should better do different project. Okay, so that we have varieties in our classes. Okay. Yeah. So what's the page limit here? So the content should be about 1.5 pages at least. Okay, at most 2-3 pages. Don't write too long. Okay. So 1.5. What do I mean? 1.5 only cover a 1.5 covering these three. Okay, first three. Okay, this content, the main content need to cover up to 1.5 pages. A4 sizes, okay, reasonable. Don't make the, don't try to make the spacing big or the word large, okay? So I mean just normal spacing and font, okay? You can have a look on the sample I put on Moodle, okay? So at most 3 pages enough. Don't go too much, okay? Uh, right. So easy to read. Okay, so at least content at least 1.5 pages. Okay. So at most you can go to 3 pages. That's all. No need to write too much. Okay. Yeah. So 1.5 pages, the idea is about 1/3 of history background, 1/3 of theory, 1/3 of example, something like that. Okay. Or you want to make your proof longer, theory part longer, and then maybe example part shorter. Something like that. Okay. Yeah. All right. Okay. Easy? Not easy. Okay. Yeah. Try don't do it last minute. Okay. Don't do it last minute. You won't be able to do well if you do last minute. Start thinking now. Okay. Then read a bit. Yes. Because my last batch of students, they like to keep everything to last minute. They just do last minute. Then they complain so many things to do. And I already give you 10 weeks ago. So you start collecting. You don't need to do it this way, but you just read a bit, read a bit, read a bit. Yeah. So maybe sometimes you need to change the culture of working now. Okay, it's not like just finish work, finish job, finish job, finish job. Okay. So sometimes the job is like very long, take a long term. So you need to learn how to divide your time. Okay. Okay. Um. Right. Should we come back to this warm-up question here? Okay, so let's look at the first question here. So does 1/4 plus 1/16 plus 1/64 plus 1/256 and so on converge? Conversion. Why? Why converge? To converge to what? 1/3? 2. Uh, you're just guessing. How you guess? Half, 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 and half. What kind of half?
Similar to the 1/2, 1/4.
Sure. Okay. So first of all, answer my question first. So why does it converge? Okay, it's a geometry series. So when does geometry series converge? R is less than 1. Or modulus R is less than 1. Okay? Maybe minus 0.5 also would. Okay? So modulus R less than 1. So what's the common ratio here? Huh? 0.25 or it is 1 over 4. Okay, which is less than 1. So it converge. Okay, good. It converge. So how to find S infinity? How to find the sum? Seng, what's the formula of S infinity? What's the formula of S infinity? A. Huh? Okay, A minus over 1 minus I. Okay, so what's it? So what is A here? Okay, what is okay? I already decide. So S infinity is 1 over 3. Okay, 1 over 3. Okay, so so last time I said that geometry series typically can be seen through geometry, right? So what kind of geometry is this trying to do? What is this geometry doing? Can you imagine the geometry here? Imagine anything useful? What is 1 over 4? 1 over 16? 1 over 64? What are these numbers? Fraction. Any special about this denominator? Any special about this denominator? Huh? Powers of 4. Sure. Powers of 4. Anything else? Else? 中义 who is 中义? Okay. Can you see anything from the denominator? Sorry? Huh? Any idea? Not really. 巧东 who is 巧东? Huh? 巧东? Oh, okay. Not here. 曾康. 曾康. Okay. Oh, Zhengkai is you. Okay, maybe I skip you first. You have been answering my question quite a lot. Okay, it's okay. Yixing. Yeah. Anything special about this denominator? Other than power of 4? How about what is 4? Huh? Yeah, what is 4? 2 to the power of 2. Okay. 2 to the power of 2. 16? 2 to the power of 4. Anything else about 16? 4 to the power of 2. Okay. How about 64? 8 to the power of 2. Okay, so they are all can be expressed as a square of certain number. right? So here we relate square to something geometric. What's a square? What's a square? When do you need to take a square? Area? Area, right? Okay. So if you have a square, what's the area of a square? Side square. Right, side square. Okay. So can you build a square with length half, 1/8, 1/4, and 1/16, is it? 25, 256, 16. Right. So what kind of a square you have? Huh? Okay. Mm-hmm.
Size of A is 104.
Okay, so let's start with a unique square this time. Last time we take a length one, right? So now we take a unique square. Okay. So how to get 1/4 here? So we divide by 4. Okay, we cut this square into 4 equal pieces. Okay, and then we take 1/4 here. Okay. Take this one. Okay, how about take 1/16? We cut another square into 4 part again. 1, 2, 1. Okay, and then we take the square again. And then we cut the top right square into 4 parts again. Okay, and then we keep doing it. We keep doing it. Okay. And then somehow you can see that when we take the area of all these squares, this converges to 1/3. Okay. So seems like these squares equally divide the square into 1/3. Okay. But 1/3 you can't really how to say it? You can't really divide 1 by 1/3, right? You always get the non-ending decimal, right? Okay. Somehow this provide you a way to cut the square into 1/3, into 3 parts. Do you get what I said? 1/3 is what? Non-ending 3, right? So where's the okay? I mean, if you cut something, right, just cut it. You don't have like non-ending, right? So where's the non-ending part go? I mean, this is like a cake cutting problem, right? Cut cutting problem, right? It's similar to the cut cutting problem. So how you cut the cake equally? Yeah,
It's a round cake.
it's a round cake. 190 degree. Yeah, maybe 3 can. How about the other number? Non-deep. I mean, it's not multiple of 3 or yeah, something like that. Right. Huh? Use the sign. Sum. What is sign? Series. Yeah. So I mean, somehow this way you can get 1/3 of cutting. Okay. Of course, you don't want to perform this cut, right? Okay. Of course, you don't want to perform this cut. So I mean, yeah, this is one way of thinking about it. Okay. Yeah. Okay. How about the next one? Actually, is this obviously infinity? Obviously infinity. Yeah, okay. Actually, we can show it using a tool we're gonna learn later. Test for convergence. Okay. So if the series converges, then the limit must go to zero. Since this limit doesn't go to zero, it should diverge. Okay. We will see the argument later. Okay. But I want to throw you a topic. Okay. I want to throw to you this topic here. This is called Ramanujan summation. So I'm not sure you read enough maths news or not, but by Ramanujan summation, okay, the sum of natural number is actually minus 1/12. Okay? Yeah, you can do this using some trick, okay, using some trick of infinite series, but there's a physical interpretation here, okay. So where is the physical interpretation? So you go to such a large number, okay. So how we physically um, interpret this, okay. So actually this has something to do with quantum physics, okay. Has something to do with the quantum physics. So when the repulsion between two metal getting larger and larger and larger, okay, until a stage when you get closer the distance, and then suddenly the metal become attractive, okay, become negative. So they attract after a certain limit. Okay, at first they repel, but when you go to a certain limit, distant limit, they somehow attract. Okay, so this is how the minus 1/12 come from. Okay. Actually, mathematically, we can also extend this series using, I think, Riemann zeta function, something like that, okay, to get this minus 1/12 solution in a complex world. So if you are interested, right, you can try and look up this Riemann summation and then write in your project. Okay. Yeah, so project 1 and project 2 can have connection, okay, because project 2 is a application, right? So let's say if you wrote this theory part, project 1 about Riemann summation, and then in project 2 you can write about quantum physics that related to this Riemann summation. Okay, there can be no connection, but you can do them as a sequel. Okay, if you are interested, I will put into my lecture note how to get this. What's the trick used to find minus 1/12? Okay. But we won't do this in class because it's not the lecture content, but it's just something for you to see. Okay, interesting stuff. Okay, so just now I said that if the sum, okay, sum of a sequence or infinite series converges, then the limit of individual term must go to zero. Okay, so let's look at this statement now. So let's start with test for divergence. Okay, so we will do quite a few tests. Do quite a few tests starting from now. Okay, so the first test you will learn is a test for divergence. So what kind of test do you want to introduce? So we want to check whether a series converge or not. Okay, so finite series definitely converge, right? You just add finitely many terms. But how about infinite series? Okay, so infinite series doesn't mean that it always diverge. Okay, it could converge. So when does it converge? So if the infinite series converges, then the individual terms should converge to zero. Okay. So left hand side, you have a series. Right hand side you have a sequence. Okay, what kind of sequence is that? That sequence is coming from the term inside your series. Okay. So conversion of the series has something to do with the term inside the series. Does that make sense? Okay. So it's like you have a A1 plus A2 plus A3 plus up to AN, but you throw away all the plus, and then you look at AN. Okay, the behavior of the sequence. Okay. Let me see. So let's quickly prove this. Okay, let's quickly prove this. Okay, so how should we start? So we want to show what? What do we want to show? We want to show that the limit of n to infinity of an is 0. Okay. So whenever I do proof, right, or I teach proof, so the first thing you want to write is your goal. Okay, your goal is very important. Okay, your goal will decide how you start, how you end. Okay, if you don't put your goal first, you will soon lost inside your argument. Okay, so put your goal first. Okay, it's like how I started this class. What's your goal toward this class? Okay, if you have no goal to study until half semester, you will be lost. Okay, so what's your goal? Keep your goal. Your goal is very important. So my goal now is I want to show that the limit of an is 0. Okay. So what do I have? Okay, what do I have? I have that the inference series converges. Okay, what does it mean? What does it mean? What's the definition of a convergence of a inference series? Sam? Yeah? Chen Jack, you want to say anything? Yeah, just say it. It's okay. What does this mean? What's the definition? Geometric series? No, no, because we start with any series here, not just geometric series. Any series. So what does it mean by series to converge? Ivan. What does it mean by series to converge? No, no. If you don't know, probably you will be gone for this whole lecture. What's a series to be converged? Hmm? Ah. What kind of quantity we are interested for series? Are you interested in series? No. Then maybe you are not suitable for this class then. Okay, how about you want to try or you don't know? Seems like you haven't wake up yet. How about Sydney? Is Sydney here? Okay. What does it mean to be AN inference series to converge? You can check your note if you like. Any idea? Hello? No idea. Okay. How about we recall what's the definition of sum of AN to converge? Okay. So we say that the infinite series converge. Okay, make sure everyone listen carefully. Otherwise, you'll be gone for this whole lecture. We say that the infinite series converges if the infinite series equal to some x, okay, where s is finite. Does everyone understand the statement here? the series equals to some number, which you can write down. Okay, for example, just now, this geometry series converge because the series is equals to the some finite number. Okay. Okay. So for a series, we are interested whether it converge or diverge. Okay. If it converge equal to some finite number. Does it make sense? Make sense, huh? Okay. So since the series converges, okay, then the series is equal to some x. Okay. Some x in a real number. Okay. All right. So what's going on here? So how is the relation between an and s? Huh? S is the sum of an, right? So if I give you the sum, can you extract an for me? For example, how to extract a1? Okay, x1 is a1. How about a2? Okay, good. x2 minus x1. In other words, what is an? Minus s? Okay, good. Okay, so we got this relation, right? Okay, so you see, what you want to compute? You want to compute a limit of an, right? Okay, so let's apply an to this formula here. Okay, to both sides. So we apply limit to both sides. Limit of n to infinity of an, and then limit n to infinity of xn minus s. Okay, so how to compute the right hand side now? You know how to compute this? How to compute? Larry. Why can I distribute? Yes, then what we use? We use the property of convergent sequence. Okay, because Sn is convergent. Sn and Sn minus 1, what's the difference? Yeah, just one go faster than the other, but they are really the same sequence. Okay, so they converge by they converge by definition. Okay, by definition, by assumption. Okay, so Sn converges by assumption. How about I check one more person, see whether you know what I'm talking about. Jingsen, why Sn converge? Sorry? Ratio is what? Hmm. Hmm? Yeah. Yeah, no, so what ratio? Why is there a geometric series coming in again? There's no geometric series here, okay? No geometric series. Okay. I think you guys are a little bit confused with infinite series and geometric series. So geometric series is a type of infinite series. Okay, infinite series doesn't need to be a geometry series. Okay, infinite series doesn't need to be a geometry series. Okay, geometry series is a type of infinite series. The reason why you keep seeing geometry series now is it's easier to explain. Okay, later you will see a lot of series which is not geometry series. Okay. So now I just want you to go back your definition. Okay, for mathematics course, right? Definition is really important. Okay, so why I can say Xn converges here? Why Sn converges by assumption? Which assumption? Any idea? Yeah, it has a finite sum. Okay, so in particular, the n partial sum converge to that finite sum. Okay, so that's why Sn converges. So Sn is the n partial sum for the infinite series. Okay, so by the property of convergence sequence, okay, we can distribute it. Okay, and then what are these limit then for Yen rule? What's the limit of these two? Okay, so each of them is what first? Sorry, each of them before we take the difference. So what's the limit of Sn when n goes to infinity? Okay, S, and then the other one we also get S. Okay, so x minus S is 0. So we have achieved our goal. Okay, so let's decide. Here is by property of limit of sequence. Okay, here is by assumption again. Okay, any question? Can you follow? Can follow? Can follow? Okay. Please ask question. Okay. Don't think that you will dread time or what. If I think that you will dread time, I will hold your question. Don't worry. But if you have question, you just ask. Okay. So the main purpose you come here is to clear your doubt. Okay, and then learn new stuff. Okay. Okay. Everyone happy or not? Okay. So please remember this statement. So if the infinite series converges, then the limit of an go to 0. Okay. But but what? But this is a P implies Q statement, right? Okay. So you cannot say that if I limit an go to 0, then my infinite series converge. Okay. This is not how you use this statement. Okay. P implies Q doesn't mean that Q implies P. Okay. But P implies Q implies what? Yes, not Q implies not P. In other words, if you check that the limit of an is not 0, then the series diverge. Okay. So typically the contrapositive of this statement is more useful. Okay, because we are interested in the infinite series, not the an. Okay, typically. Okay. So let's try and apply uh, this test. So let's check whether this series conversion. Okay, I'll let you try about 2 minutes. Try see if you can check this conversion. Yeah, try check whether this series conversion. Done. You said done. Okay. What do you do?
I set the XM first.
Okay, you set a okay. Sure. So what's the AN? Mm-hmm. Okay, so this is the AN. Okay, so we start with this AN, then we compute the limit of AN. So what should you expect before you calculating? What should you expect? If the AN is 0, can you say anything? No. Okay, you cannot say anything if it's 0. If it's non-zero, can you say anything? What can you say? The series diverge. Okay? So that's why the test is called test for divergence. Okay, although you don't see any diverge word in the statement, but the control positive is about the divergence. Okay, so let's compute this limit here. So how do you compute this limit? Infinity over infinity. Okay, so you can divide by n cubed. And you get 1 over 3 plus 2 over n. And then in this case here, huh? Take what? Take both. Uh-huh. Okay. Okay. Yeah. So this is the limit of sequence, right? Okay. So you can apply everything from what you learned from the sequence. Okay. And then you will get 1 over 3. Okay. 1 over 3 is not 0. So by test for divergence, the series is divergent. Or the series diverges. Okay, the series diverges. Okay. Okay, next one. So next example is a quite famous example. All of you should know. So this is the harmonic series. Okay. You can see that this harmonic series is not geometric anymore. Okay, not all its series are geometric. Okay, so this is not geometric. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. Okay, prove that this is divergent. For harmonic, any one of you play music or not? Any one of you play music? You play music. You are Zheng Kan, right? Zheng Kan. Okay. So these are about the wavelength of a tone. Okay, overtone. Okay, half overtone, one overtone, 1/3 of a overtone. Okay. For example, you can think of it as a vibration of a string. Okay, how you imagine the vibration of a string? So you can have a 2 wall and then with 1 string, something like that. And then I think half is something like this. Is it? And then if I remember correctly, something like this, if 1/3, 1/3 of a string. Does anyone know? I mean, harmonic series is also one very interesting topic you can write for a project. Okay. Yeah. Okay, so these are about a wavelength. And so harmonic series diverge. But what can you see here actually? What can you see here? So what's the limit of this AN? Going to 0. Okay. So actually you can't say anything, right? And in particular, this is the counter example of the inverse. Is it inverse? Inverse of our statement just now. Converse or inverse? Converse. Yeah, converse, right? Right, converse. So P implies Q. So let me write down. Q implies P is the converse. Okay. So but the harmonic series diverges. Okay, so these provide a counter example for the converse of test for divergence. Okay. So why does this diverge? How to show this diverge? Okay, how to show this diverge? I think we need to go back to Gauss. Okay, let's see how we show this diverge. What did Gauss do? Okay, so he regrouped these terms. Okay, how to regroup these terms here? Okay, how to regroup these terms? So we keep 1. Okay, we keep half. Okay, and then what we do here is we want to make it greater to something that we know it diverge. Okay, so we want to make it greater to something that diverge, then surely the series also diverge. Okay, so what we do? We make it more regular. Okay, we make it more regular. So we can group this term like this. Okay, so what's the benefit of doing this? So we can make 1/3 greater than 1/4 this way. And similarly, we can take 1/5 up to 1/7 greater than 1/8. And then why are we doing this? Let me show you why we are doing this, then you will know what is the pattern. So if we do this for 1/3 and 1/4, the 2 1/4 will add up to a half. Okay, and then 1/5 to 1/8, then also half, right? There are 4 terms here, which is greater than 1/8. Okay, 4 times 1/8 is half. Okay, it's another half. Okay, so how do we group them? We group that such that it is greater to a sum that is half. Okay, so in this case, we will replace 1/9 is greater than 1/16, and then you should imagine there are 8 of them. Okay, 8 times 1/16 is another half. Okay. So you can keep performing this operation infinitely. So 1 plus a half plus a half plus a half plus a half plus a half. Okay. Which you will get a sum that is growing larger and larger. Okay. Sum that larger and larger. As n goes to infinity. So the harmonic series is divergent. Okay, so this is a very important example you need to know. Harmonic series diverges. Okay. Okay. Any question up to here? No? One more. You want to take a break or you want to go longer a bit? Take a break? Okay. Okay, let's take a break. Okay, let's come back at 4:04.昨天那个做出来了
啊，昨天那个就后来那个样子就能做出来。
？OK。
是 diverge 吗？
没有 convert 下
这个 converge 吗？
，convert
哦，这个 converge。
convert 去0，对
OK，
convert 对，然后呢？
然后那它是 diverge。
这个啊，
可以下来一点东西吗？
哦，你要 promote 它？
下礼拜，下礼拜，
哦，
下礼拜，下礼拜。
哦，下礼拜什么意思？你要干嘛？
没有，下礼拜我要 promote 费嘛？
这个时间呢？你
，break
来
time 吗？还是上课前？还是
对啊，你下礼拜3天，
下个礼拜你们上
我们是
好像是跟
3天上。
3天上
Yeah，
？OK，可以啊。
OK，可以。
OK，
OK，
我得到我只是要确认人数吧，因为我跟 Peter 讲。
OK，
哦，这个 control positive。对，加油。
OK。哦，这个 diverge 吗？哈，
对
这个是 geometry series 是不是？啊，对，所以 geometry series 什么时候 convert，什么时候 diverge？
是 diverge。
对，geometry series 最前面看 ratio 要小于
小于
1，
1
对，所以你的 ratio 是多少？
是2/2哦，那这就是 converge。OK，还有一个最后没有听懂。
哦，你说这个啊，
对啊
这个，
对啊，
哦，这个我是说by 这个东西吧，我没有说它怎么来，但是我会 share 在 lecture note 我会 share 它怎么来，我没有说它怎么得到它，我只是说如果用 Riemann summation 就可以得到这个数字。
为什么是这个数字？
为什么是这个数字？
对啊，
为什么是这个数？你可以
这个叫什么 summation？
Riemann summation，
我回去找一下。
yeah，你可以玩一玩这个 series， 这个 series。
OK， 对，我拍到了。
我会 share 啦，我会 post，
OK，
如果你要拍，但我会 post， 呀，我会 post，
OK，
我会 post 上去。
那这个有道理吗？或者他会用到吗？
道理就是 quantum physics， 就是量子力学会用的，呀，量子力学里面会用的，呀，或者说我们在 consider 不一样的space 的时候就会用得到，
用了。
我们去到 complex 的时候。那个哦，你不看没分出来。
这我放在你问题。
OK，
可以帮我看。差点一点都不见。
So OK 了，我先做我的，看一下，做。哎，不然我直接讨论啊，你们三个坐在那边，我直接讨论，我直接放在这边，我直接放在这边，反正现在休息一下。Okay, someone asked me about how to find the limit of 1 plus 2 over n to the power n. How about x? Use x. Okay, how to find this? I think the answer given is e to the power square. Okay, this is one of your textbook question. So how to find this? What you can do is you start with uh, yeah, actually what can you do, right? Let me think what's the natural way to plan. Okay, how about we look at this limit instead. Okay, so let y to be 1 over x. Okay, so we somehow invert the limit to y. Okay, so if x go to infinity, y go to 0. Okay, so y go to 0 if x go to infinity. Okay, so we invert the limit. 2y to the power 1 over y. Okay. So that's a factor of e, right? So how to do it? So you can't really take limit of power. Okay, so somehow I want to throw this power down. Then how I throw this power down? Huh? Logarithm, ln. Okay, we can use ln, maybe we use ln. Okay, so instead of studying this, maybe you can study this function instead. Because the advantage of doing this is I can throw the limit down. Sorry, throw the power down. Okay, throw the power to the front or multiply by the power. Okay, right. So, but to this stage here, I think this is easier to see what is going on. Right. Okay. Top go to where? When y go to ln 1. Where's ln 1? Ln 1, 0, right? Okay. Bottom also go to 0. 0 over 0 is 0 over 0 is 0. Okay. Okay, 0 over 0 undefined. Okay. So so what should you do? Huh? L'Hopital. L'Hopital, right? Okay, we can use L'Hopital rule. So how to use L'Hopital rule here? So L'Hopital ln 1 plus 2y is what? 1 over 1 plus 2y. So y divide, differentiate, you get 1. Oh, so 2 over 1 plus 2y, yeah, correct. Okay, yeah, good. So bottom you differentiate to 1. Okay, so this is what you get. So this limit here is pretty obvious, it's just right. Okay. So how to get e to the power 2? E on both sides. E on both sides. Sure. Let's see what happens if we apply e on both sides again. So e on both sides. Okay, but the left-hand side here is not quite what we started with, right? So can we bring limit down? No. No, then there's a problem. I can. So I can. Why can't I?
And then you can use the logarithm rules in the x one.
So you mean this one? You want to do something on this? So you mean like this? Like this? Okay. Then yeah. You mean this? Like this?
Yeah.
And then
We can actually like evaluate the power first.
why? Why? Why can you bring the limit up? It's the same question here, right? Why can you bring the limit down? Hmm? We don't know yet. Yeah. E is constant. No. No. You shouldn't look at E. You should look at E to the x. Y equals to E to the power x is what? Is a function, sure. Is increasing, sure, increasing. Another important property is a EX is a no an adjective. What kind of function? Who say one? Continuous function. It's a continuous function. Okay, so continuous function you can bring the limit in. Okay, so you can swap the limit of E ln E plus 2 by 4. Yeah, so you will get this, and then you apply the change of variable back again, then you will get the original x limit. I think like this. Does everyone follow now? So we can bring the limit down or in because E is continuous everywhere. It's a continuous function. Yeah. So if a function is continuous, then you can bring the limit in out. Don't buy the argument. Remember last time we introduced the sequential continuity? If AN converges to L, okay, and then F is continuous, okay, F, the limit of FAN is F of the limit of AN. So you can bring the limit into the function if the F is continuous at that point. Yeah. I mean, so okay. So let me write a little bit more. Okay, let me write a little bit more. Okay. So we see that limit of this sequence here converge to 2. Okay, so what we need here, why we can bring the limit down, limit up, is because e to the power x is continuous at x equals to 2. Okay, it is continuous at the limit. Okay, let me recall the statement for you. Theorem. So if an converge to L, okay, so you need to think of this as your an now. Okay, an converge to L. Okay, and what? And f is continuous. Okay, continuous at L. Okay, now we continuous at 2. Ex is continuous at 2. Okay, what is going on here? Then what? Then the limit of f apply to an, right? Ex apply to this thing, okay? And then you take the limit, okay? Is equal to what? F on the limit on the sequence. Make sense or not? See, limit outside, limit inside, limit outside, limit inside. Okay? Okay. Or do you know Ex is continuous at 2 or not? You know, right? What's the shape of Ex? There's few basic shape you need to remember. Ex is one of them. Okay, Ex is like this. Here is 1. Okay, so 2 is around here. Where this point here is e to the power 2. Continuous, obviously. Okay? Okay? Okay, so need to apply, apply what you learn. Okay, understand what you learn. Okay, don't just follow and then do it. Okay, yesterday I already tell you, need to understand. Okay, understand. So how to understand? Okay, one way is you use it. Okay, use it, practice it. Okay, I need to practice. Okay, any question? Okay, okay, can. Okay, yeah. I mean, this question, right? This problem, every year will come up one. Yeah. Every year people will ask. Just a little bit tedious to explain. Okay, let's start. Hey, by the way, let me take attendance first. So we have Go Fan Ye, right? Okay, I know Go Fan Ye already. Yu Yuan. Okay, Jing Shen, Chen Jack, Ivan, Ziying, Larry, Lo Hao, Zhong Yi. Okay, Zhong Yi. Qiao Tong. This one's okay. What happened? Accident. Huh? What happened? What happened to her? Huh? Yeah, what happened? How? Don't know. Accident. Just like that. Okay. Mistake. 曾汤、宜兴、若山、Roshan. Roshan disappeared for 2 days already. Han Wei. Yeah. No. Another one first. Tao Han Wei first. And then Han Wei. Okay. This one left for Sydney. Yeah. Yan Ru, Roland, Han Wei, Zhou Jing, and Yu Xiang. Okay, good. All right, so next, we also have, previously we have a property of convergent sequence, right? Now we also have property of convergent series. Okay, we also have convergence of series. Okay, so similarly, we start with two convergent series. Okay, so two convergent series. And then we also have a constant. Then what do we do? Okay, then do you know what we're gonna do? Multiply. Okay, we want to multiply also. Okay, we want to create new series. Okay, we can create new series like C times AN. Okay, what is this sum supposed to be? C times the infinite sum. Okay, so this is right, right guess. But this only work when AN, the series of AN converge. Okay, it doesn't converge, we don't know. And then what else we can do? We also can take the sum or difference of individual term between AN and BN. And then you can just split the sum up. So what's this property again? Last time I called it. What's this property again? These two. Start with L. You can pull constant out. You can split sum. Start with L. When can you pull the constant out? When can you split sum? TCX equals to CTX. Tx plus y equals to Tx plus Ty. Linear, okay? So summation is linear, okay? So this shouldn't be surprising, right? Summation is linear because you can just factorize stuff, okay? But this one is actually quite surprising, okay? You have an infinite sum, okay? Why? You can rearrange them. Okay, this is something special here. Why can you add all the AN first and then add all the BN? But here we mix them up. Okay, here this is a big special thing. Yeah, but this one is just factorize all the C. But second one is a bit special. So I shouldn't be surprised that sum is linear because you can factorize sum. Okay, another thing is conversely. Okay, conversely, if the sum of AN diverges and C is a non-zero constant, then okay, CAN also diverge. Why we require C not equal to zero? Chin Z, do you know why? Why we require C not zero? If C is zero, then we will just get a zero series, which converges. Okay, so we want to throw away that example. Okay, good. So similarly, we won't prove this. If you are interested, you can try and prove in the project. So we're gonna learn how to use it. So let's compute the following sum. 1 over 4n squared minus 1 minus 5. Okay. How can you compute the sum? How to compute the sum? Any idea? How to compute the sum? So this is the difference of two sequence. Okay, difference of two sequence. So what's the first sequence? Anyone still remember? The telescopic sum. Okay. So last time we compute that the telescopic sum equals to what? So, oh yeah, sure. Okay. I mean, how about the series? How about sum? It's just Yeah, correct. So you just take the So okay. So this infinite sum is okay, sure. So the n partial sum of this guy is a telescopic sum. Okay. So to get the n partial sum, you just take the first term plus the last term. Okay. But here we are looking at the s infinity. So you take the limit of the Sn. Okay. So after we take the limit of the Sn, what's the result? The result is just half. Okay. Last time we get half. Okay. You forgot, you should go back and check. It's just yesterday. Okay. How about the second term here? Does this series converge or not? What kind of series is this, Ivan? What kind of series is this? The second geometry series. Okay, with ratio what? What's the ratio? Hey, hello, excuse me. Hey, talk to me. Don't talk to your friend, talk to me. Yeah, ask me. So what's the ratio of a geometry series? Sorry? 1/3. So there's an extra 5 here or how? Okay, so the first term we have this, and then the second term we have this. Okay, sure. Yeah, okay. Yeah, so the second term have a ratio 1/3. Okay. And so diverge or converge? Converge. Why? Because the ratio is less than 1. Okay, good. Okay, so this converge to where? Converge to where? How to compute? Han Wei, to compute the sum. Take the 5 out. Okay. Can you take the 5 out? Huh? Yeah, can you take the 5 out? Yeah. Huh? You want to? Yeah, right. So yeah, it's not you want to. Okay. Sometimes if you want, you cannot do. Okay. Because 1/3 and converge is a geometry series, so you can pull the constant out. Okay. Then you use the S infinity to compute, which is A over 1 minus R. Okay. So in all together, you get 5/2. If you don't want to pull it out, also can, right? You just straight away use apply A over 1 minus R. In this case here, what does it mean? It means that this 5 will go to the top here. That's all. Okay. So you see, so you pull the 5 out, pull the 5 in, will mean different thing. Okay, different operation. Okay, although they are the same. Okay, so good. So this is a difference of two convergence series. So that means we can split the sum up. Okay, we can split the sum up using the property just now. A linearity of the convergence of series. So we can split the sum. And all together we will get half minus 5/2, which is -2. Is it surprising why if you add up number you get negative? Surprise or not? No surprise. It's normal. 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 You add number and then you get negative. Normal or not? Normal. Both thing is positive, right? Normal. Normal.
We are genius.
Huh?
We are genius.
What do you mean, genius? Yeah.
Let's move on.
I mean, yeah. So that's mean one sum is bigger than the other sum. Okay, next. How about this? Sum of 1 over 3n. Does this converge or diverge? Huh? Diverge? Why diverge? Diverge or converge? Is this a geometry series or not? No. Okay. Converge or diverge? Diverge. Why? Harmonic series. Because of harmonic series. So how do you see harmonic series here? Okay. We can take 1 over 3 out. Okay. So we use the converse statement just now. Okay. If the harmonic series converges, okay, and then you multiply. You multiply by a constant. Okay. You multiply by a constant inside. Then 1 over xn or c times an also diverge. Okay. So let me write it down. Since the harmonic series diverges, harmonic series n, okay, and 1 over 3 is non-zero, okay. So by property of convergence series, by convergence series, then the series of 1 over 3 times 1 over n also diverges. Okay, right? Yeah. Yeah, so this is how we use these properties. Okay, next. So, there's a remark I want to make here. Okay. So a finite number of terms does not affect the convergence or divergence of series. Series. Okay. So what do I mean by this? Okay. So let's start with the example last time, right? So if I have a half plus 1/4 plus 1/8 plus 1/16, so on. Yeah. We know that this converge, okay, equals to some x. Let's say if I remove the first few term, okay, does it still converge or not? Does it still converge? Yes, right. Huh? It just take away this term from your final sum, right? Okay. So similarly for divergence as well. Okay. So if the series diverge, okay, you take away finitely many terms, it still diverge. Okay. Otherwise, you can get the limit. Okay. So this is also the similar property you observe in sequence. Okay, in sequence. So sequence, right? So like what I told Vincent yesterday, right? So let's say we have a sequence converge to L. Okay, we have a sequence converge to L. If I remove the first few terms, okay, from the sequence, it doesn't affect the convergence of my sequence. Okay, because convergence of a sequence, what's the convergence of a sequence? What's the definition? Okay, last time I asked Laura, Does Lohao still remember? When does the AN convert to M? What's the definition? Cannot give it. What's the definition of a sequence convert to M? So I give you two keywords. Oh, you want to say or you want a keyword? Okay, I give you a key phrase. So the key phrase is arbitrarily close and large enough. One is arbitrarily close to one. One is large enough. Others can try and recall what's the definition. Okay, don't just wait for answer. Try and recall yourself. Yeah, you want to try? Try first one. Wrong, never mind. Just try. I give you a few words lah. You make a sentence for me. Yeah, make a sentence. See how creative you are. Just try anything come out of your mind. You want. Huh? I'll try. Hello. We have to finish on time. I'll try. Just say. No need check. Yeah. So you take 5 minutes. Get this slide. Okay. So AN converges to L if AN get arbitrarily close to L when N is large enough. So what does it mean by N is large enough? Okay. It means it is at the tail of the sequence, at the back. Okay, or we call it a tail of the sequence. Okay, we only care about the tail of the sequence. At the front, what happened doesn't care. Okay, the front, finally many terms we don't care. Even if it jumps, no matter how crazy, we don't care. Okay, what we care is about the end or the tail. It doesn't end because it's go to infinity, but the tail of the sequence matters. Okay, so you can see these two behavior appearing in a series, both series and sequence. Finite term, we don't care at the front. What we care is the term at the back. Okay? Because what is important is at the back. Okay? We still have infinite term to consider. Of course, it will for series it will affect the sum. Okay, but it won't affect convergence or divergence in general. Okay. Yeah, question? Either terms can or not? Wow, you don't want cancel front term, you cancel middle. Okay. As long as it is finite, that's fine. Okay? As long as it is finite. Okay. Because let me show you. Last time we have one example, right? I think Ivan liked this example a lot because Ivan tells me got two limit, -1 and 1. Okay. So if I delete the top guy, okay, then the sequence suddenly become convergent. You get what I mean? So if you remove finally many, still okay. If you what did I say? If you remove finally many, yeah. If you remove finally many, still okay. If you remove infinitely many, then something will go wrong. Huh? Sorry? The convergence will change. Right? At first there's no limit, right? Because it jumped between -1 and 1. But if I delete infinitely many of 1, then I only left with -1. Then the sequence will converge. Okay. Can or not? I get it. I get it. Yeah. You can do whatever you can do division on finite terms only. Yeah. Okay. Finite. So the key point here is finite and infinite. Okay, not the position, but the finite and infinite. Okay. Yeah. If you want to take middle also can, but finitely many. Okay. You cannot take infinitely many. You will change your sequence. Okay. Okay. Yeah. Sure. Any question or not? No question. Okay. So far, okay. Okay. Next, we will do integral test. Okay. So let's start with the integral test. So since we have integral here, so that means we need to do some integration. So what kind of integration here? Okay. So should I give you a statement first? You want to see example first, or you want to see statement first? So in typical maths class, very classical one, they will throw you an abstract statement first, and then they give you an example. But in the real in the real work, when we do research on mathematics, typically we will start with example first. After we do this example, and then we try to abstract the idea and then get the thing. Yeah, I mean it's a different way to look at things, but you should get used to both ways. Both you need to learn. Okay, so you want an example first or statement first? Statement, okay, good. I found out that your class is a little bit different from the other maths class. The other maths class is more practical. You want to see example first. Yeah, if you start with abstract nonsense, they don't want to listen. Then they're very quick confused already. Okay, so let's start with abstract statement first. So let's start with what do you need for integral test. So you need a continuous, okay, and a positive and decreasing function. Okay, need these three property. Continuous, positive, and decreasing. Okay. You know what's continuous, right? Okay. How about positive? Always greater than 0. Decreasing. Okay, so it's a decreasing function. using function on the interval infinity. Okay, and then this is a function, right? But we have an in our infinite series. So how to cook up this an here? Okay, how we cook out this an is to just take f apply on natural number or the positive integer. Okay, or positive integer. Okay. You can see that our interval is from 1 to infinity, so it includes the integer in particular. Okay. So what should we imagine here? So last time I give you a sequence and then I ask you find the limit using the real, right? But now instead you start with a real, okay? You start with a real and then take the discrete point. Okay, so there's an order change here. Okay, you start with a function and then you take the sequence an. Then what? Okay, so quickly we have the result now. Then the infinite series an, okay, is convergent if and only if the improper integral of fx, okay, fx from 1 to infinity converge. Okay, if and only. So if you know that your an infinite series an converges, then the integral also converge. If the integral converge, the infinite series also converge. Okay. So can you imagine what we are doing here? What are we doing here? So one of them, you are taking the sum of the height. Okay. The other one, you are taking the area under the graph. Okay. So obviously, one sum is bigger than the other. Correct or not? Is it correct? Is it true? So one of them, you just add out the in Malay we call tiang, but in English we call paw. Okay. So you just add out this stick or paw here, right? You take a discrete sum. But the other, you take the area under the graph, right? Right. The integration of the function. So which one is bigger? The integration always bigger, right? Okay, but somehow these two will control each other. Can you imagine? Can. Okay. But you still have some extra stuff, right? How can you control the stuff enough such that we both converge and then we both diverge? How about maybe one converge, one diverge? Because you have more stuff, right? But somehow, yeah, we can control each other. I mean, this is the idea of this statement. We haven't proven yet. Okay. So this is the idea that this statement trying to give you. Okay. You get what I'm trying to say? Okay. Okay. And maybe we will see example later. We'll see example how they control each other. Okay. But anyway, the point here is how can the stick control the area? Okay, so in other words, I don't want another word already. So I think you should get it. Okay, you should get it. So let's look at example. Again, look at example, then we will know how they control each other. Okay, let's see how we use area under the graph to control just the discrete value. Okay, so look at one example first. One example we want to look at is the sum of 1 over n squared. Okay, sum of 1 over n squared. So what is this sum here? So this is 1 plus 1 over 2 squared plus 1 over 3 square plus 1 over 4 square, and then so on. By the way, this is different to the one we started. Okay, the one we started, we pick a special square. It's like a square of 2, 4, 8. Is it? Yeah. So now we take the sum of square of 1 over square of natural number. Okay. So so what? So the statement says, okay, if the integral version of this function converge, then this limit also converge. Okay, let's compute. Let's compute first. Let's compute what is the integral of x squared. Okay, how to compute this? So this is an improper integral, right? So by right, you need to use the improper way. Okay, use the limit. Okay, in this case here should be easy. Okay, should be remind you on calculus. So what's the integral? Minus 1 over x. Okay, from 1 to t. Okay, in this case here, you take the limit of minus 1 over t plus 1. And this is just 1. Okay. So this means that the integral converges. So by the integral test, the infinite series also converge. Okay, so how do we see this? How do we see this actually? So how do we see this? So let's draw some picture. Let's draw some picture. Okay, so our function is y equals to 1 over x squared. Okay, 1 over x squared. And then the sum start from 1. 1 over x squared start from 1. So we should start with when y equals to x equals to 1, y equals to 1. And then it is decreasing. So why can we use integral test here? Because it is continuous, positive, and decreasing. Okay. So so how do we see the sum? How can we see the sum here? The sum here. How can we see the sum here? One way you can see is from the height. Okay, like what I said just now. You look at the height, right? So you look at the height here, and then you look at the height here, and then you look at the height here, right? And so on. Okay. But there's another way to see this is if you multiply 1 to this height, did you do anything to the height? No, right? Okay. But there's one advantage of doing this. You can realize this number as an area again. Okay, area of a side of 1 times the height. Okay, so I can make this into an area like this, where these are all with side 1 and then height of 1 over n squared. So it becomes an area under the curve again. Yeah, but you can see that this is not quite the area under the curve, right? It's just approximating because there's an empty space here. Okay, but this part is an extra part. But what did we say just now? What did we say just now? So even if we remove the finitely many term, the convergent series still converge. Okay, so if it converge here at the bottom here, we add another term, it still converge because just add some finite number to your final sum, right? Okay, hello. Question? I see some confused. Yeah, things I want to ask. Oh, I thought you're a bit excited, so you want to ask stuff. You want to ask something. Any question? No. Okay. So from this picture, actually, what do you get? Okay, let me write down what I say just now. Okay. So what we have is actually just sum from 2 to 1 over n squared is less than integral of 1 to infinity of 1x squared dx. Okay. So we only have this, right? Because we only computed area under the graph from 1, starting from 1. Okay, so we have this. So we know that this sum here has to be less than 1. Okay, so must converge. So what happened from the sum starting from 1? Okay, what we do is we just add an extra term to it. So we add 1 to our sum from 2. Okay, but we know that this term is less than 1. Okay, so in total, the original sum will be less than 1 plus 1, which is 2. Okay, still converge. Okay, so the sum of 1 over n squared. Okay, and so just now how we go from the height to area, we just add a box with a side 1, and 1 times the height is still the height. Okay, so this is how we realize a number as an area. Okay, 1 is very useful in mathematics. Please take note. 1 is very useful because 1 is the identity, multiplicative identity. Okay. Okay. Question? No. Okay. Let's do. Let's see. How about we finish the example of integral test before, only then we take the rest. Okay. Okay. Next. Next. So next we will look at this 1 over square root n. Okay. Take the series of 1 over square root n. Okay. What are we going to do this time here? Okay. Similarly. Okay. So to use integral test, right, you need to check the tree property. Okay, actually you need to check the tree property. Do you know how to check or not? Should I? Okay, let me go through first and then we'll see. So first property, you need to check that this function is continuous. Okay, continuous at where? Continuous at 1 to infinity. Okay, so do you know how to show this? One way is to use definition, epsilon delta definition, but I don't want you to get into that. The other way, you can use a composite of continuous function. So meaning we already know what kind of a function is continuous. Okay. So for example, we know x squared is continuous. Okay, we know that 1 over x is continuous away from 0. Okay. Right. So this domain is away from 0. So composite of continuous function is continuous. Okay. Yeah. Yeah. Did you guys learn this or not? Composite of continuous function is continuous. So let me write down here. Composite of continuous function is continuous. Okay, so you compose x squared and 1 over x together, and then you will get 1 over x squared. Right? Why seem a bit blur one you? So so I set f equal, okay, don't want that. Okay, use f. F equals to 1x, g equals to x squared. So fgx is what? Is 1 over x squared. That composite of continuous function is continuous. How about positive? Okay, positive I think quite straightforward. Okay, 1 over x squared is always positive. You divide by a positive number, and x is greater than 1. Okay. decreasing. Usually decreasing will take some work. Okay, decreasing will take some work. So decreasing here is similar to the decreasing in the sequence, right? Okay, so what do I mean by decreasing here? So decreasing here means for y greater or equal to x, okay, we will have for all y greater than x, we will have f y is less than equals to f x. Do I want equal or not? Maybe I shouldn't take equal. Okay. Otherwise, I will have a constant function. Okay. So if my y is further, okay, my fy should be lower. Yeah, my y should be lower. Okay. Yeah. So when my y is further, when my x is further, my fx should be lower. Can get it? Okay. So should we check this? Should we check this? So let's check whether 1 over x squared minus 1 over y squared is greater than 0 or not. Or greater than x. By the way, I want to remind you guys, right? Because my class sometimes a bit like experimental. So I will go into something that I like or I don't like on the spot one, spontaneous one. Okay, so you need to learn how to cope with this, or you need to learn how to deal with this situation. Because why? Because in a real situation, when you go out and work, or even when you talk with your friend, right? You know what your friend wanted to talk to you, what he gonna say to you. Of course, you straight get the information and then process it, and then you give feedback to your friend, right? Correct. Okay, so in mathematics course, it's also like that. Okay, but it's more technical. Okay, it's not some gossip or what. It's more technical. Okay, so you need to learn how to take in this spontaneous information. Okay, because why? Because why I say so? Because in mathematics we have definition. Okay, we have logic. Okay, if the logic is not right, then you will know something is wrong. You know, okay. Actually, this also help you, okay, to discern what people say, whether that guy, that person's what he says correct or wrong. Okay, you don't just take everything what he said is true, or you believe everything what he said. Okay, correct. You get what I mean? Okay, I mean maybe you don't have this ability yet, but slowly I hope when you go through this maths course, you should have this kind of ability. Okay, so this is what maths course will train you. Yeah, I also don't realize this at first, but somehow when I go through PhD learning these abstract stuff, different abstract stuff, and suddenly when I listen to what people say, eh, somehow I have a different feeling to what I listen to people. Yeah, you somehow will know, oh, this person maybe is talking about that stuff. Not directly what he is trying to say or she is trying to say, but he is trying to like how to say, what's the English word for insert? You know what's insert? What's the English word for insert? Huh? Dark? DARK? No， 影射来影射不同的事情，来 foreshadow not quite right foreshadow. Yeah, you go. Okay, so So I mean, yeah. So yeah. I mean, this is a skill you need. Yeah, this is a skill you need. Okay, this is a skill you need. You really need. Okay. Actually, especially I am talking to the back one, because you guys didn't listen to me. So be careful, be careful. Yeah, at the back. Be careful, I'm talking to you because you are not listening. Okay, have you found it or not? Huh? What's that? This INNU.
Yes.
Is there a verb? This is the nouns, right? Is there a verb?
I see it's
Yeah, I thought insert is a verb. Ah, okay, then maybe we need a verb. I think this word is right, but I want a verb. Yeah, or you can search a thesaurus for this word. Okay, yeah. Okay. 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 Let's continue. So, is this true or not for y greater than x? Uh, we are not quite there yet, so maybe we need this term here. Is this true? Okay. So what do I have on top? Difference of square. Difference of square as well. Formula y minus x times y plus y. That right? X, yeah, x. Is this correct or not? This formula. Correct? Correct? Okay, over x squared. X squared. Okay, so we turn the first question to the last line here. Is this correct? X and y, where does x and y live? Other than 1. Okay, so obviously the denominator is positive. This factor here is positive. How about this factor here? Y. Y, yes, yeah. Okay, so we have 3 positive things multiply and divide together. So this term is positive. Okay, yeah. So in the proper argument, you should show me f is continuous, f is decreasing, f is positive. Then you can use the integral test. Okay. Yeah. So sometimes in the lecture, okay, I don't want to say, but yeah, you need to show this. Okay. Okay. Next. Next. So should we do the same or not? If we gonna use if we're gonna use the integral test. So continuous is the same argument here. Okay, so we look at 1 over square root x is continuous on 1 to infinity. Okay, because it is a composite continuous function. Okay, 2. I think this is strictly positive, so it's quite easy to see, right? So this one is easy. How about decreasing? Is it hard or not? So we need to take 1 over square root. So for y greater than x, we take 1 over square root y. So the other way, which way? Square root x minus square root y have to be greater than 0. Okay, because the previous one is higher than the one that come after. So is this true or not? I'm not sure. Let me check. It should be true, but I'm not sure we can do it or not. So let's try the same technique. Oh, you're quite fast, eh? Oh, very fast of you. Very good, very good. So this means you are very attentive. Okay, so what we can do is instead of breaking up, we introduce a new factor. Okay, we introduce a new factor here. Actually, this new factor is good. Why is it good? Root y plus root s is still positive. Okay, yeah. But the numerator even better. It will become y minus x. Okay. So the denominator is still positive all the way, but the numerator is also positive due to the assumption. Okay, yeah, good, very good. All right, so let's start the integral calculation now. Okay, so let's compute this integral here. Okay, typically this integral shouldn't be hard to compute. Okay, so what's this integral? Okay, this integral here is just 2 square root x from 1 to t dx. Okay, no more dx. Okay, and then this is what? This is just 2 square root t minus 2, which is infinity. Okay, so you can use integral test to deduce that. So by integral test, the infinite series of 1 over square root n diverges. Okay, because the integral diverges. Okay, but how we see this? Okay, how we see this? So go back to geometry again. Yeah, let's go back to geometry again. Let's go back to geometry. So our function now is 1 over square root x. Okay. Similarly, we have this pole here. Okay, or we have a tiang here. Right. Maybe also it's good for the Chinese to learn what is tiang. You know what is a tiang? Yeah, tiang is a Malay word for 柱子. Okay. Yeah. So if you heard people say 撞tiang, is a 撞到柱子. Tiang. Okay. Okay, good. So yeah, so there's a height here. Okay. How we see a divergence here? So we want to realize as an area again. So what kind of area you want to have? Want to put? Do you want to do the same thing as previous? Like this? Like this? What if you do this? What if you do this? What if you do this? So just now we compute the area under the graph is infinity. Okay? And then your boxes is inside this infinity. So what can you tell about this boxes? You cannot tell anything. Right? So can you do something else? Huh? Yeah, I did. I did. You draw something. What's that? Outside the box. Outside the box. Okay, maybe we can try. Instead of that box, we take a different box. Maybe this box. Okay, this box. This box. Okay. Why is it good about this box here? Because this box cover the infinite area. Right? Okay, this box cover the infinite area. Okay, so this implies that our infinite series also diverge. Okay, so this is the idea of the integral test. Okay. When you do this question, you don't need to draw this diagram, but this diagram will tell you how the integral test work. Okay, why the integral converge, your infinite series converge? Why your integral diverge, your infinite series diverge? Okay, so it's because you pick a different. Oh, why you didn't tell me at the why all my box gone? And next time you need to tell me if my box disappear. Okay, no wonder you look very confused. Okay, yeah. Okay, so you see your box cover the infinite area under the disappear again. Oh, okay. I think I know what's going on because it doesn't like my scribble. So I scribble slowly. Yeah, yeah. Because good note 6 is not very good. Okay, some function is good note 6 is not very good. If you can, don't buy. I want to buy because I hope there's a new feature coming out. Yeah. Okay. I will spend so long time on this. So how about I keep the one for exercise. So I keep one question for homework. So homework is about this series here. Sum of 1 over n squared plus 1. Okay, try and use the integral test on this. Test it with integral test. And I will provide solution. There's a remark under the test which I will provide later. You can read about it, or I'll make it a question next time. We'll come back again. Okay, how about we take a break until 5 to 1. Okay, 5 to 1. Yeah.
就是一个从微观到点的一个问题啊。因为就是为什么如果你要证明一个这个 n 啊，就比如讲用 limit，然后某个方圈它是用 n 啊，然后你用的是就是你用这个来证明，就是用 x，并就是用任
那个是一个 theorem 来的。
I mean，如果我的这个方向我可以用某个方法做出来，为什么我还要用到这个方向，然后再把它整出来，然后再 impress 这个东西？
因为是这样，就算你 告诉我，我真的知道这个 sequence 是什么，我真的知道这个 sequence 的 limit 是什么，那我也不能够相信你。
只要by theorem 就对了。
一个是 by theorem，一个是 by definition。OK，definition of convergence。但是我们的 definition 呢，刚才那个 arbitrary close 跟 enlarge 的那个 definition 呢，不够 rigorous，就是不够 rigorous。
我懂。
比
precise
较 rigorous 的是用 epsilon delta，除非你用 epsilon delta 咯，告诉我咯，它可以 epsilon 靠近 L，when I adjust 那个 n 咯。
哦，
不然呢，你就要用另外一个方式来告诉我了。然后我用的方式是说，你可以用这个 theorem，就是说，如果你会算这个东西，这样你就知道它的 limit。但是当然，我也没有告诉你为什么这个 theorem 是对的咯，对不对？所以，yeah，我只告诉你有这个工具吧，我没有告诉你为什么这个工具可以用。
哦，
Yeah，
我是有一个就是那个昨天那个，我还是问你那个保证的问题，就是假如我的 AN 大过1，
对
它就是没有保证的，它已经超过那个线了。那你讲的 Q 越来越高，越来越高，越来越高，就是那个 AN 是 increasing，
你要 AA increasing，然后
，AN 是 increasing，
然后
然后讲它这个保证在这边，保证在，
bounded 是要两边的，bounded above 跟 bounded below。
比如讲我是保证有办法，就是那个 E 嘛，昨天有，
那个是 bounded below，
你
你讲它在它上面嘛，所以它下面是 bounded by E，对不对
不是在它上面的那个 AN，节目越来越高
？AN 在它上面嘛，我们现在是指的是 AN 嘛？AN 的下面，
I mean 就是
你换你
就是你昨天那个
我昨天忘记了。
哦，就是你讲到，比如讲 A 呢A 2，我讲这些是保的，
所以你看这个 AN 在它上面嘛，所以它下面是被 bounded 的。
为了你先画我下，画完然后你讲它是隐蔽性的哦，
对
然后当它超过的时候，你记得吗？
，OK，超过 OK 呀，超过
这个时候这样它就已经是没有保的了。
它没有 bounded above，所以呢，它没有 bounded，所以呢，
然后
它没有 bounded
讲
above，
过的时候，
啊，
讲，等一下，等一下，对，我会讲的是，因为如果他就会一直你讲的你给的解释就是他不是恐怖圈的原因，就是因为他一直在 increase，
对，没
但他
错
不他是越离这条线越来越远，
，yes，
但是我可以不可以证明他已经是没有保的了，他已经不保的，他已经超过这个条线了，他就没有保的办法。
然后你要做么呢？它不 bounded above，然后你要证明什么？到最后，
通过证明这个保的他没有保的合法化，这样他就是divergent，不是吗？
它没有 bounded above，它就 diverge。
因为他意思 increase 啊，离这条线远，
是
这样，
是这样，
哦
是这样，是这样，
我也可以用这个来 prove 吧。
可以，
还有
可以，我觉得，
还有那个 assignment 的题目，assignment 的题目我有点看不懂，不知道我们有没有学到。
OK，
我有一个很困难的，I mean 就是会问很久一下，我想很快。
还有3分钟。
我不知道，我还没有学到这边呢。
哪一个？
这边的这两个，这两个我
还没有学，还没有学，
还没有学，
还没有学，这个字还没有遇到。
哦，radius of convolution 我就看到
还没遇到，还没遇到。我们才刚刚进 series 嘛，应该要在后面一点点。test 过后， Shall we start? Don't have much time left. Okay. Shall we start? Yeah. Finish discussion. Okay. Next we'll deal with P series. Okay, we deal with P series. Okay, so what do I mean by P series here? So let P be any constant. Okay. And just now we look at 1 over n square, right? Okay. Now we look at 1 over np. Okay, 1 over np. So this is called a P series. Okay, 1 over np. So this P is referring to the power. Okay, power of your denominator. And the series we take is natural number. Okay, 1 over natural number to the power P. Okay. So when does this converge? Okay. So for series, we still want to ask question. When does it converge? Okay, when does it converge? So we're gonna prove this. So we will prove that the P series is convergent. Okay, is convergent. If and only if. What's your guess? When does it converge? You already see example, right? What example you see just now? P equals to 2 converge. Okay. Equals to 2 converge. So if and only if P greater than 1 actually. Okay. And the harmonic series diverge. That harmonic series is when P equals to what? Harmonic series to 1. Okay. So 1 also diverge. Okay. So probably we split at 1. Actually, we're at 1. So this segment here is the if and only if, right? Okay. So if I'm going to prove this if and only if, I need to prove 2 direction. Okay, we need to prove 2 direction. So let's prove from right to left first. Okay, maybe this one is easier. So suppose P greater than 1. Okay, suppose P greater than 1. So what kind of technique we can use? What kind of technique we can use here? So remember, what's the rule I say in mathematics? So we introduce tools or object we need to use next. So what's the previous tool we introduced? And just 10 minutes ago. Integral test. Okay, integral test. So let's see if we can use the integral test or not. Okay, so in this case here, we want to show that P series converge. In other words, we want to look at fx equals to 1 over x to the power P. Okay, so is this continuous from 1 to infinity? Yes, right, because it's a composite of continuous function. Is this positive or not? Positive or not? Positive, right? Because you just take power of positive number from 1 to infinity. How about it decreasing? Decreasing. Yes. How? No. How? Decreasing. Do you want to compute 1 over xp minus 1 over yp or not? Now here p is any real number greater than 1. So how are you gonna deal with all the different p? Just now we used property of square, different of square, right? But now you got p, got p maybe 1.1, 1.2. How? Huh? Binomial. Actually you can, I think. Actually you can use binomial. So later we will touch on this binomial series again. So yeah, binomial actually extend to real number, I think. Yeah, but there's another way to show decreasing here. Okay, on the spot I'll tell you. So it's to show that f prime x is less than 0. Okay, always less than 0 for all x in 1. Okay, because the gradient is less than 0, so it's decreasing. Right. Okay, so what's the gradient of this function? What's the gradient? Ivan, what's the gradient of this function? What's the derivative of this function? Yeah. What's the derivative of this function? Negative. Differentiate x to the power minus k. Yeah. 1 over x to the p minus 1, like this. Multiply by p. Okay. Yeah, this one. Okay. So p is positive, x is positive, p minus 1 still positive because p greater than 1, right? This right. Where's my p? P plus 1. Plus 1 or minus 1? Plus 1. Okay, plus 1. Then p plus 1. So p plus 1, okay, is still positive. P is positive. X is positive. Okay, so minus a positive number is negative. Okay, so this derivative is always less than 0. Okay, so now we need to check the integral. Okay, from 1 to infinity. So what is this? So you integrate this, you should get x to the minus p plus 1 over minus p plus 1, which is going from 1 to t. And then this limit here is just what? We can do this first, 1 over 1 minus p, and then 1 over t, p minus 1, minus 1. Okay. And then from here should be easier to see, which is 1 over p minus 1. Okay. Can follow? Okay. Okay, so this is finite. Okay. P greater than 1, so p minus 1 is some number. 1 over some number is still finite number. So the integral is convergent. Okay. So by integral test, our P series also converge. P series also converge. Okay. 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 Next. Next we need to prove the other direction. Okay, the other direction. The other directions means what? Which direction? From left to right. Okay. That direction means that if P converges, P series converges, then P is greater than 1. Okay. But instead we're doing that, okay, we will do contrapositive. Okay, proof by contrapositive. So if P is not greater than 1, then my series diverge. Okay. So if my is my P not greater than 1, how many cases do you have? Then my P is, okay, let me write first. Suppose P is not greater than 1. Okay. So this means that P is less than or equals to 1. Okay. P is less than or equal to 1. Okay, so we need to show that if P is less than or equal to 1, then the P series diverge. Okay. So we can split into few cases. Okay, we can split into few cases. For example, P equals to 1 is obvious. What is P equals to 1? P equals to 1 is just harmonic series. Okay, so diverges as harmonic series. So how to show harmonic series diverges? We need to use the Gauss method to group the number together so that we get a lot of half adding up together. Okay, another region you can split into is between 0 and 1. Okay, between 0 and 1. Okay, between 0 and 1 here, we can apply integral test again. Okay, we use integral test again. So let us recycle our calculation. And recycle it. That's very useful. So we don't need to check integral test condition anymore because we already do it before. Okay, so when P is in between 1 and 0, what is happening? Huh? What happened? Infinity. Why? Why? P minus 1 is smaller than 0. Okay, so P minus 1 here is smaller than 0. Okay, so this T go to the numerator. Okay, so it should out to infinity. Okay, so by integral test, our series also diverge. And P diverges. Okay, still has few more to go. P less than or equal to 0. Okay, so let's deal with P equals 0. What happened when P equals 0? You're just adding up 1. Okay, you're just adding up 1. Okay, so actually, how to show this 1 divergence? Okay, you can use infinite many 1 to say, but there's a test you can use. 1 times n. What do you mean 1 times? Oh, 1 times. Oh, you mean look at the look at the limit of n partial sum. Okay, yeah, right, correct, true. Okay, you can look at the limit of n partial sum, or you also can use divergence theorem. Okay, you also can use divergence theorem, right? If the limit of an is non-zero, then the series diverge. Yeah, there are a few ways you can check. Okay, how about p less than 0? P less than 0, how? Goes up. Okay, you mean the an, n in the an, right? Okay, so this thing will goes up. So what do I mean by goes up? It becomes n to the modulus of p, like this. Okay, so what's this? The limit of this is infinity, not 0. So by what test? Divergence test. The p series diverge. Okay. Okay, good. Very good. Okay, good. Let me see. Maybe we skip. Okay. Yeah. So this is p series. So the main takeaway here is the p series converges when p is greater than 1. Okay. Don't confuse with geometric series. Okay. So geometric series you need ratio less than 1. Okay. P series you need p greater than 1. Okay. Don't confuse these two things, because later we will have comparison test, so you need to compare with different series. Okay. Yeah. How about I skip. Let me skip one subtopic. Can I don't want to teach because it's quite applied. Since we spend more time in the proof in this class, right? So maybe I make it more pure a bit. Can or not? Can I? Okay, you agree? Okay, so make it more pure. Okay, but this section don't throw away. I let you read. Okay, let's say if you read it, you don't understand. Okay, we come back to lecture again. We take it back and then we do it together. Okay, otherwise you absorb yourself. Maybe I won't test heavily on those things, or maybe even I won't test on those things. Okay, but let's make this course a bit pure. Okay. Okay. Because sometimes things to apply a bit awkward when I teach. It's like counting, just counting. Okay, like not much content. But anyway, if we need it or if you don't understand, we can always come back again. But I will put it into the lecture note. Okay. So whenever I put into the lecture note, you can read it. If you don't understand, please come back to me. Okay, come back to me. And then if I think it's really important, then I will discuss again in the class. Okay, but for now, I skip it. So let's go to another test. Actually, there's another example on integral test. Okay, so maybe I left this as a homework. Okay, homework on this ln n over n. Okay, this example is quite interesting. Okay, you should try this example because it doesn't decrease starting from 1. Okay, start somewhere else, but it still works. Why? Okay, try first. Okay. Like what I said just now, first few terms throw away, never mind. As long as the thing afterwards converge or diverge. Okay. Yeah. Try this. If you don't understand, then we will do it in lecture again. Okay. Try this. This one quite important, because if I do it in class, I think spend a lot of time. I'll pause solution and then you can check. If you still don't understand, and then we can discuss. Okay, because doesn't it's important. So next, let's get to a comparison test. Okay, so let's get to direct comparison test. Okay, let's get to direct comparison test. So suppose that we know AN is always less than BN, less than or equal to, and then both of them are positive. Okay, this is quite important, quite important point here. Both of them are positive. Great. After certain big N, okay, we don't care about finite term. Okay, after certain big N is enough, right? This is our philosophy here. Anything in the tail works for everything. Okay, anything works for the tails, works for everything. Okay, if it works for after a big N, then what? Then the series of Bn converge implies that the series of An converge. Okay. Similarly, if An diverge, then the inverse series of Bn also diverge. How should you imagine this situation here? This is a bit similar to integral test, okay? But now you only compare two Tian, okay, two poles, right? An and Bn, okay? So if the lower one, if the smaller one diverge, okay, it will somehow like push Bn away. Okay, Bn also diverge. But if the series of Bn converge, then An is somehow squeezed by this Bn. Okay, so An also converge. Okay, so this is how you should think about this statement here. But how are we going to prove this? Okay, how are we going to prove this? How are we going to prove this? Yeah, how are we going to prove this? Actually, this proof is very interesting. Okay, it uses what you have learned. Okay, it uses what you have learned. Okay, this proof is very interesting. So let's prove the first statement here. Can you see that the second statement is implied by the first statement or not? Second statement is the contrapositive for the first statement. Okay, so just prove one of them. So suppose Bn is convergent. Okay, suppose Bn is convergent. Okay, we want to show that the sum of An also converge. Okay, yeah, so what to do? What to do? So series converge, right? What's the definition of series converge again? Let me change another person. Just now we checked about sequence, right? Okay, try Zheng Kan this time. What's a series to converge? Yeah. Definition of a series to converge. Series converge to L means what? In the form instance and as it goes to infinity to zero. This zero? So what does it mean by a series to converge? Mm. Ah.
And partial sum.
Okay, and then. Oh, okay. Yeah, okay. Okay, good. Okay, good. Okay. So this is the other definition. So the infinite sum converges if the partial sum if the partial sum if the n partial sum converges. Okay? If the n partial sum converges. In particular, this converges to the value we give to sum to infinity. Which is the most important thing is which is finite. You cannot say I converge to infinity. There's no such thing. Please don't write this in the exam or assignment. Converge to infinity. Okay, there's no such thing as converge to infinity. That's diverge. Okay, which is finite. Okay. Yeah. So like this. Okay. So what do we have now? So you want to show an also converge, right? So you need to check the n partial sum as well. Okay. So let's set some term. So we have an n partial sum of ai. Okay. And then we have n partial sum for vi, series of vi. And then we have the sum, the actual sum. Okay. Because it converge. Okay. So we know that Tn will converge to T by assumption because infinite series converge. Okay. Now we want to ask whether this an converge to some let's say x or not. Okay, this is what we want to find. All right, we want to prove. Remember what we want to prove? Infinite series of an converge. Okay. So this is what we don't know. This is what we know. We don't know. We know. We want to prove. Okay, we want to prove this using this. Can understand or not? I'm just translating this two line here. Okay. Suppose the infinite series converge. Okay, we got this. We want to show that the infinite series of an converges. This is what we want to show. Converge to some x. Okay. Does everyone follow what we have and what we want to prove? Okay. So we turn the convergent property to the n partial sum, conversion of n partial sum. Okay. Actually, this is almost by definition. You can take this as a definition if you like. Okay. So how on earth are we going to do this? How on earth am I going to do this? Huh? How am I going to do this? Hmm. Hmm. Let's try let's write down what we are given, okay? So what do we have? So we have an greater than 0, bn greater than 0. Okay. Is it strictly or yeah, just greater or equal to 0? Okay. And then this in this case here, what does it mean? when I look at the n partial sum, okay, when I look at the n partial sum, okay, this partial sum is what kind of sequence? You keep adding new positive number. So they are increasing is strictly right. Okay, this one is a bit weaker, can be 0 sometimes. So it is non-decreasing. Okay, non-decreasing. It is not decreasing. Okay, but it is not increasing as well. So sometimes it stays constant. Okay. Okay, all right. So you know that these two are non-decreasing. Okay. So non-decreasing is a monotonic sequence. Monotonic sequence. Is it? This part of the monotonic sequence. When does the monotonic sequence converge? You want Sn to converge, right? So when does the monotonic sequence converge? If it is bounded. Okay. Can we see whether if it is bounded or not? Then can we check whether Sn bounded or not? Already monotonic, right? We just need bounded. Okay, bounded means what? Bounded below and bounded above. So is Sn bounded below or not? 0, right? Okay, bounded below by 0. So very obviously, so we have Sn is bounded below by 0. Okay, how about bounded above? Is it bounded above or no? Bounded above by Tn. Okay. If you say it's bounded above by Tn, so the bound, when we say bounded above or below, that bound has to be a constant. Okay, cannot change term by term, Right? Cannot change term by term. Okay. Is it bound by a constant? No? Yeah. Is it bound by a constant? So let me write down what you see. So we know that A1 is greater or less than or equal to B1. This implies that Sn is less than or equal to Tn. But is it bounded by a constant or not? Is Tn bounded by a constant? Why? That's not quite the reason, right? Because you can approach from the top. Because this is a non-decreasing function, sequence. Okay, so it's non-decreasing, and then the limit is t, so it must be less than or equal to t. Otherwise, you can reuse my argument last time. Remember the example? Why the an cannot greater than 1, cannot greater than the limit, right? Okay, or you can use that argument. Okay, so because Tn is non-decreasing, okay, and then it converges, then Tn must be less than or equal to T. Okay. Yeah. So because Tn is non-decreasing and Tn is no, and Tn converges to T. Okay. So either it is T, either it is less than T. Okay. So it's bounded above by a constant T, which is the limit of my Bn, and then bounded below by 0. Okay, so in this case here, we are good now. So hence Sn is monotonic and bounded. So by the monotonic sequence of theorem, An is complete. Okay. Okay or not? Okay. Hey, how about we do one example and then we finish? Okay. Otherwise, I scared you forget this statement here. Okay. Let's try one example and then we will break off. So example. So look at this series 5/2n squared plus 4n plus 3. Okay. Determine whether this is converged or not using a limit, using comparison test. So for comparison test, what is the tool you need? You need a 0, okay, greater or equal to 0, and then less than or equal to some bn. Okay. And then you should know something about this bn, right? You should know something about this bn. Or you need to produce an an, and then you know something about this an, then you can deduce for bn. Okay. So can you compare this series to some other series that you know? Try spend some time thinking about it. Yeah, any series you know. What kind of series we know? We know P series converge when P is greater than 1. Okay. We know geometric series. Okay. So can we compare to any series or not? Okay. What kind of P series? N squared. What P series you want to try? 5/n squared. 5/n squared. So 5/n squared live on which side? Which side? This side or this side? N squared is less, right? So must be greater. Okay. So I think it's on this side. Okay. How about left hand side? Do you have 0? You have 0, right? Obviously, because n is 1 to infinity. So what do we know? We know sum of 5/n squared is convergent. Okay, why? Because of P series when P is equals to 2. Okay. Actually, you have an extra 5 here, right? P series start with 1/n squared. But this 5 here can be deal with the property of convergent series. Okay. And property of convergent series. Okay. So so what? So by the direct comparison test. Okay. Comparison test. The series 5/2n squared plus 4n plus 3 converges. Okay. Yeah. Yeah, so you can go back and try another example, which is the sum of ln n/n. Okay. Check whether this converge on average. Okay. Any question about these tests? Any question? Any question? No? Okay, then we will see you next week. Next week. Okay.